All right, so chapter 11, we're going to learn about the different properties of solutions. Now, this means more on the molecular level, how do solutes and solvents interact and what effect does that have on specific things like boiling point, freezing point, on vapor pressure, and other things like that. So, and also properties of solutions, meaning the concentration and other things. So we know there's various types of solutions, and the definition of a solution is a mixture of, it's a homogeneous mixture of a solute and a solvent. So the solute is dissolved in the solvent, and you can have different types of solvents. You can have liquid, gas, or solid solvents even. For a solid example would be an alloy, like we talked about last week with brass. So you can have a solution that has two solids that are mixed together in a homogeneous fashion. So you can also have solvents that are polar and nonpolar liquids. And we're going to talk more about that, but a common polar solvent is water. And then you can have nonpolar solvents like hexane or dichloromethane, things like that, that do not have a dipole moment, like we talked about for intermolecular forces. They don't have those. And we're going to learn that the reason why, I'll tell you right now, the reason why that oil doesn't mix with water is because oil is nonpolar and water is polar. So likes don't like to, or dislikes, things that are different from each other in terms of polarity, don't like to mix well together. If they have the same intermolecular forces and the same polarity, they tend to mix more frequently and they dissolve in one another. There are solvents that can dissolve a whole range of polarities, though. There's kind of middle ground. There's a whole spectrum of polarity. Things that are really polar is water, and things that are not so polar, you have things I mentioned, benzene, hexane, cyclohexane, things like that. But you can have a middle ground. And one of these common solvents that is good to know if you go into chemistry that we use for a lot of different things is called DMSO. So DMSO. It's called dimethyl. Wait, this wire's in the way. Hold on. Dimethyl sulfoxide. And it's kind of it's half polar, half nonpolar, and it can be used to dissolve many nonpolar organic compounds and also things like salts, and it can dissolve in water too. So it has a it's kind of in the middle ground, and there's a lot of other solvents that are in the middle ground. So just to know that, I mean, just to refresh everybody on what solutions are. So now solutions have a main way of concentration, main way of determining concentration, and we have mentioned this. We've danced around molarity this semester, but we know that molarity is the moles of a solute divided by the liters of the solution. So it's a very simple formula, and it's big M. So it's important that it's big M because we're learning about another one that's little m called molality. And they're similar, but there are different ways of determining concentration. Now, the molarity is the number of moles of solute per liters of solution. So that's very important to know. And pretty easy to figure out. You guys should have a grasp of how to do that. Then you have other ways of determining concentration, and they all start with M. So that's funny. They have mass percent. Mass percent's a very easy one. That's not a good straight line. Mass percent's an easy one that we've been exposed to already when we were learning about molar mass. So we've done questions like in iron sulfate, what is the mass percent of iron? So in that case, you would take the mass of iron, the molar mass of it, divided by the molar mass of the whole thing, and that would be a percent. And the same thing applies here. If you have a solution that has a certain mass of a solute, you can divide it by the mass of the total solution, multiply it by 100, and you get a mass percent. That's another very valuable way of determining concentration. You also have the mole fraction, which we've talked about when we talked about partial pressures and different things about gases. The mole fraction is the number of moles of one substance divided by the total moles in the solution. So again, it's a fraction. And then you have this one where we haven't talked about yet, and it is a new one called molality. So it's kind of like if you say molarity with a lisp, you say molality. So it's different, and it has a little m. And molality is the moles of solutes. That's the same, whereas molarity is moles divided by liters. The moles of solute is the same. But instead of the liters, we have kilograms of solvent as opposed to liters. So here's a fun question. why do we need, so what's the difference? Why would we want one over the other? Now, liters, so if you, and think about this in the context of gases. Let's say you have a balloon or any closed chamber with gases in it, and you have a certain number of moles of that gas. The moles are going to stay constant. So I'll just give you that as a hint. So anybody have any ideas of why we would use molality as opposed to molarity? Or what's the difference that you see? Why would the difference be important between doing the kilograms of solvent versus the liters of solution? Anybody? I know it's December, but you could do it. Yeah, so why, okay, I'll repeat the question one more time. Why would we use molality as opposed to molarity? The moles of solute are the same, meaning it's in the numerator, but the kilograms of solvent versus liters of solution. Why, can you think of anything why we would use one over the other? Yeah, so Daniel, that is a good point. So we can go off of that. Pressure differences. That's a good idea. So more specifically, well, that's kind of the answer. So what happens when you have pressure differences? So let's say we have a piston and we have this solution is in a piston. So you have a specific moles and you compress, and let's say it's 2 liters. You compress it, and now the volume is 1 liter. That changes the concentration. So the molarity depends on the pressure, and it depends on, more specifically, the volume, right? Because volume's in the equation. So it depends on the volume, meaning for gases, the volume constantly changes with response to the temperature, the pressure, and other factors too. Well, really temperature and pressure. If you can keep the moles constant, it's the only thing that changes it. But that's the point. That molarity, there's factors that can change the volume. When you're dealing with molality, if you do the same thing, you have a specific amount of moles in a piston, and then you compress the piston, you put more pressure on it, the kilograms of solvent will stay the same because you're not releasing any. It's the same number of molecules. You're just compressing them. So molality is a better standard, even though we use molarity more, molality is a better standard because it takes into, it is indiscriminate, it's not responsive or doesn't change. I can't talk today. It doesn't change with response to other factors like pressure and temperature, whereas molarity of gases does change. So Isaiah kind of the opposite. So molality would be more of a definitive answer for not gases. Or so molarity would be good. I mean, I guess it could work for everything. I mean, both of them could work for everything. But my point is that molarity would change a lot when you have gases. If you heat up the gas or you increase the pressure or decrease the pressure. So just important to know the difference. One, molality is more absolute because it strictly depends on moles and kilograms, which are amounts. It depends on the mass and the molar amount of the stuff you have, whereas molarity depends on liters. Okay, moving forward. So let's do an example. So a solution is prepared by mixing 1 gram of ethanol with 100 grams of water to give a final volume of 101 milliliters. Now this one, since you guys have been quiet, there's gonna be a lot of interactive stuff today. So there's gonna be a lot of questions that you'll have to do. Now, so you can take a couple minutes and do this one. Calculate the molarity, the mass percent, the mole fraction, and the molality of the ethanol in the solution. So I will give you maybe 5 minutes to do that, and then we'll go over it. Well, no, less than 5 minutes. Maybe like 3 or 4 minutes to do that, and then we'll go over it. All right, let's get started. So the first one's molarity. So for ethanol, I'm going to need you guys' help here. So what is the molar mass of ethanol? Good, 46. Awesome. So we have 1 gram of ethanol. So it's 1 divided by 46. That would give us the moles of ethanol. So what was that? Anybody want to divide by 46 or 46.07, whatever you got? Okay, cool. So 0.022 moles. We can divide that by our liters, which is 0.101 liters, because you need to convert milliliters into liters. And what is that answer? Does anyone have it? Good. I got 0.218, but close enough, just rounding. 0.125. Okay. Cool. So that's the molarity. Nice. Mass percent. So the mass percent is the mass of ethanol divided by the total mass of the solution. Now, the mass of the solution is not 100 grams. It's 100 grams of water plus the 1 gram of ethanol. So it's going to be 1 gram of ethanol divided by 101 grams of the total solution. That's an easy one. 1 divided by 100, about 1%. So 0.0099. Oh, well, percent-wise multiplied by 100, you have 0.99%. Okay, then the next one is going to be, where's my eraser? It's not working. Next one's going to be mole fraction. I guess we'll do it over here. So the mole fraction, we have the moles of ethanol. How many moles of water do we have? So 100 grams of water divided by the molar mass, what is that going to be equal to? Good, 5.55. Nice. So we have the moles of ethanol is 0.022 divided by 0.022 plus 5.55. So you can imagine it's going to be a very small mole fraction. And what do we get for the mole fraction? About 0.004. Sounds right to me. 0.004 equals this mole fraction. Okay, nice. And then the last one is molality. So we need the moles, which we have, divided by the kilograms of solution. So the kilograms of solution, we know the grams of it is going to be 101 grams, right? So we know the kilograms is 0.101. So it's going to be the same as the molarity in this case. And sometimes you have that when you have water involved because the density of water is about 1. So the milliliters will equal the grams. If that's the case, then usually the molarity and molality will be very similar. And it's going to be kilograms equals 0.218, and we use lowercase m for molality. Okay, good. And I'm not sure if many of you are doing these. A lot of other professors have like polls and different questions that you have to do to get credit. I don't do that because I don't want to. But again, it's on you. So if you don't do these and you don't participate in them, you're going to see the effect on your exam grade. And some of you already see that if you don't pay attention, you'll do worse. So it's very important that you follow along and do the questions. And I'm not going to baby you by giving you mandatory questions for attendance or things that you have to fill in. But I mean, you guys are adults, so you should be able to handle it. I know it's tough with this semester, but we're in the home stretch. So let's focus. All right, so we got the molarity, we did that. Mole fraction, molality. Okay, next one. So this one I kind of gave you the answer a little bit already. In a 0.1 molar solution of NaCl in water, which of the following will be closest to 0.1? The mole fraction, the mass fraction, the mass percent, the molality, or all of them? What do you guys think? No answers, really? We just talked about it. So keyword is in water, right? What do we know about water? It's density. A, not A. Good guess, but it's not A, unfortunately. So the mole fraction, NaCl, I mean, you're going to have 0.1 molar solution of NaCl. That means, so yeah, Isaiah is correct, molality. So I mean, you can figure these out on your own, the mole fraction, mass fraction, but the molality, you're going to have 0.1 molar. That means 0.1 moles in 1 liter. Now, 1 liter of water is approximately equal to 1 kilogram because of the density is about 1 gram per milliliter. So the moles will stay the same for the molality. And then the 1 liter is now 1 kilogram. So the molality will be very, very close. It'll be almost identical. Okay, moving on. So the steps involved in making a liquid solution. Now, we don't really think about this. We kind of just think they mix together. But more specifically, here's what goes on. There's three different steps. The first is that the solute gets separated into its components. And if you have a salt crystal, you're going to have the Na, let's say you have NaCl, the Nas will break off of the Cl once it's dumped in the water. And we talked about how different ionic solutions dissolve and really how any weak electrolyte or strong electrolyte or non-electrolyte dissolves. So what will happen is in a polar solution, the negative charges from the oxygen will attack the positive charges or the positive ionic charges or the positive partial charges of the solute. And then the negatively charged hydrogen will attack the positively charged, the positively charged hydrogen will attack the negatively charged ions of the solute. So that's what I mean by expanding the solute. So we're going to rip it apart. Then we're going to expand the solvent, meaning overcoming the intermolecular forces that are in the solvent. So in the solvent, let's say you have liquid water, you have a big network of hydrogen bonds. This network of hydrogen bonds needs to be broken in order for the solute to integrate into this network of intermolecular forces. And in order for this to happen, the intermolecular forces need to be the same. whether it be ionic, dipole, they need to have that same charge-oriented configuration, or they need to have no charges at all and be a kind of a very weak transient London dispersion interaction. So it greatly helps in terms of energetics and thermodynamics to have solute and solvent have the same type of intermolecular forces. And even if it's dipole, dipole, and ionic, those are compatible with each other. So that's what we need to do. We need to expand this network of and break some of the intermolecular forces to allow other intermolecular forces of the solute to integrate with the solvent network. Then you'll, step 3, allow the solute and solvent to interact to form the solution. Right. So that kind of, obviously, that's kind of obvious there. Now, those steps are actually differentiated. So steps 1 and 2 are endothermic, because what you're doing is breaking bonds, right? You're expanding the solute, meaning separating the solute into its components. You are breaking ionic bonds, even, well, in most cases, yeah, ionic bonds, and you're breaking apart intermolecular forces of the solute. So if you have a sugar crystal, you don't have ionic bonds in there, but there's something keeping the sugar crystal together. And those are dipole forces from the adjacent sugar molecules. Those have to be broken for it to dissolve. For this to happen, energy from the water is transferred to break the solute particles and break them apart. Then expanding the solvent, same kind of thing. You're breaking intermolecular forces, a whole network of them that are in the solvent. That is also endothermic. But then step 3, allowing them to intermingle, is exothermic, because the energy in forming those bonds, in forming the new network of intermolecular forces, is then releases energy. So if you ever mix an acid and a base, or if you mix a lot of salt, where is a good example? You can do this at home. You can get like maybe a cup of water, mix, maybe not table salt, but like if you can find like magnesium sulfate or things like that, a lot of it, and just mix it together in the water, the cup will actually get warm. This is because the entire process is exothermic. Because to make this new network of solvents, you're forming a lot more stable interactions than you started out with. So this is, again, the entire theme of this class is to increase energetic favorability, meaning if atoms or molecules or elements are at a higher energy level, making a solution in this case brings them to a lower energy level. And that process releases energy because the energy has to go somewhere. And you can actually calculate that by just adding up the different enthalpies of changes in the different steps. And here's a good example of that. You have your energy of you see this one's exothermic. So because the energy that you start out with, the energy of the solution is lower than it. Sometimes the energy of the solution could be higher, but most of the time it's lower because you need, it's gonna be more of a favorable solution. Okay, so factors that favor a process, we talked about this already. So increased probability of the mixing states when a solute and a solvent are placed together. This basically means likes dissolve likes, meaning polar dissolves polar, non-polar dissolves non-polar. And processes that require large amounts of energy tend to not occur. This goes into the whole theme of the course, where things tend to happen in nature that are energetically favorable and leave atoms and molecules in a energetically favorable state. Okay, so here's examples of if you mix different polars and non-polars together, what will happen. So if you have a polar solute and a polar solvent, that's favorable. So the delta H would be large. You're breaking a lot of, delta H1, I mean. So you're breaking a lot of the solute intermolecular forces. Delta H2, you're breaking the solvent forces. Delta H3, you're mixing them together. So it's going to be a large exothermic reaction. So it'll get hot. And then your delta H will be very small overall. Well, it depends. It could be negative or a little bit positive, but usually it's negative. And your outcome is a solution. When you have non-polar and polar, you have no solution. Non-polar and non-polar, you have a solution, but there's less going on. So generally, when we're talking about polar things, ionic things, when you have charges, these are stronger forces we're involving. The same thing occurs, but they're stronger. So it makes sense that our enthalpies are generally going to be larger. When you have nonpolars, we only have to contend with breaking and forming London dispersion forces, which we know are very weak. This is why for any change in the formation of the solution, we have a very low enthalpy level. And then we have, for polar and nonpolar, obviously we're not going to have an interaction. We're not going to have a solution forming. Okay, so a really cool separation technique that, well, I'm not going to dwell on too much, is called TLC, called thin layer chromatography. And this is a technique that is used, it's very prevalent in organic chemistry. And really, if you get into chemistry, you're going to have to know this technique. And what we can do is we can separate any kind of mixture into its individual components, whether they be polar or nonpolar, based on their polarity. So if two things have very similar polarity, but they're different structures, we can't separate them well, but using this technique. But a lot of things tend to have different polarity. So what would happen is there is a huge variation between there's different phases called stationary phases and mobile phases. But let's get to the actual point of it, is that you can put a solvent. So this plate is a silica plate. Silica is polar. So what will happen is if you have something that is polar, it will tend to stick to the silica more. Then you can have a solvent that's on the bottom. The solvent will ride up the silica due to adhesion. It'll just ride up. And what will happen is once the solvent goes up, it will bring the individual components in the mixture of the dot, because what we're doing, this dot comes from a solution. So you take a mixture, you take it and you dot it, you physically dot some of the liquid on the plate, and you'll see once the solvent rides up, the different components of the solution will separate based on their polarity. So what will happen is the more polar parts will stick to the silica more, and therefore they'll move up less. The less polar ones will not want to stick to the silica more because the silica is polar. So you're not going to have much of an interaction between something that's nonpolar and the polar silica, which means the less polar molecules will have an easier time riding up the plate. So at the end of the day, you can have a whole spectrum. If you have a really dirty mixture, you can have 4, 5, or 6, maybe even whole streaks of different molecules that are in the mixture. But ideally, you want to have 1 or 2 if you're trying to separate something. So we use this a lot for organic chemistry to validate whether our reaction worked. So if we want to react, so here's a reaction that I've been doing lately, is I want to take something that has like a double ring structure, like this. It's more complicated than that. It's kind of polar. It's got some oxygens on it and some nitrogens in there. And I'm trying to mix it with this, that's not it. So with this group, which has nitrogens on it. So generally, and also it has like other shit on it. Oh, I said shit, whatever. It has other shit on it too. But it makes it polar. So this group, once we add it to here, would make it more polar. So I did a reaction, and now the step is to see based on this TLC, if I have 2 dots, and I do. And I have a more polar dot, which is probably my product, this combined with this. And then I have a less polar dot, which is most likely this. And then I have probably another dot, which is, well, I think I do, it's very light, of just this alone, which is kind of lower. So we can rank things based on polarity and see what we have in the solution or in the mixture. So it's a very powerful technique. It's very sensitive too. You can put a couple of microliters on the plate and it'll work. So it's actually really cool. Any questions on that? No? All right. All right, so, answers are here already. So for each of the following pairs, predict the substance that would be more soluble in water. Now, for this one, you have pH3 and NH3. Why would NH3 be more soluble in water than pH3? So now that we know the answers, now we can see, all right, why is that the case? Anybody have any guesses? Think about Lewis structures, think about polarity, thinking about electronegativity. What do we got? Yes, more polar. Good job, James. So it's more polar because nitrogen is a lot more electronegative than phosphorus. And if you look at the numbers, phosphorus actually has the same electronegativity number, 2.1, that hydrogen does. But the molecule is still technically a little bit polar. And that's because of the lone electron pair and the sizes of phosphorus and hydrogen. But NH3 is very polar in comparison. So that's why it would dissolve more frequently and easier in water. Now, what about for B? We have the first one, right? Yeah. So the first one. So anyone guess why the first one is more soluble than the second one? CH3C. This is acetic acid. And yes, it has the OH. Good. So Johnny, getting to your point, OH means it's more polar. So here you have an OCH3. A methyl group, a CH3 group, tends to make a molecule less polar. So you can kind of see with a lot of these organic structures, it's really a balance of polarities. So if you add things that are more nonpolar, the molecule itself becomes more nonpolar. If you add things that are polar, it helps it dissolve in water. All right, so which of the following chemical or physical changes is an endothermic reaction? So this is kind of random, but I mean, it applies. So what do you guys think? Endothermic, so combustion of gasoline. Is that going to be endothermic or exothermic? That's going to be exothermic, right? And we have an answer. Alex says B, and that is correct. But yes, I think we all got the point here. So I'll explain them. So yeah, obviously combustion of gasoline is going to be exothermic. We're releasing a ton of heat. We're burning something. Freezing of water. The water is going from a higher energy state as a liquid, more movement, more kinetic energy of the molecules, to a lower energy state as a solid. Therefore, energy is released exothermically. And then if we're mixing sulfuric acid and water, we're going to have some fizzing. We're going to have, again, this is a mixing of, so we're breaking the intermolecular forces between the water, and we're mixing in sulfuric acid to make more stronger forces. So what this is going to do is going to release heat. And then we have evaporation of water. We're going from a lower energy state to a higher energy state as a gas, meaning we have to put energy into this. So B is our correct answer. All right, the next thing we're going to talk about is Henry's Law. So this talks about the pressure, or how does pressure affect solubility. And so we didn't really, I don't like the way this chapter is separated. It is in the order of it. So let's talk about solubility first. Solubility. So the way I like to define solubility is a threshold of dissolution. Threshold of dissolution. So what this means is that every solvent at a specific temperature and pressure has a solubility of a specific solute. For example, and this solubility level is a threshold. For example, if I say that, if I say that the solubility of NaCl in water at 25 degrees Celsius, 1 atm, is 2 grams per milliliter, this means that the maximum amount of solute, NaCl, that I can dissolve in 1 milliliter of water is 2 grams. If I put in 1 gram, that means another gram could dissolve. If I put in 3 grams, that means only 2 will dissolve, and there'll be 1 left over as a precipitate. It'll still be solid. It won't dissolve at all. So this solubility is a threshold. Once the threshold is met, no more solute can be dissolved unless you change one of these 2 factors, temperature, and more dealing with gases, pressure. So is there any questions on what solubility is? On what I just said? I kind of went through it a little bit fast. So it's a threshold of how much can dissolve, how much solute can dissolve into a specific solvent at, let's say, room temperature, 1 atm. Good? All right. So when we go to Henry's law, we talk about those factors being temperature and pressure, but in Henry's law, more specifically pressure. So Henry's law states that the amount of gas dissolved in a solution is directly proportional to the pressure of the gas above the solution. So the best way to talk about this is Coke cans or any carbonate or beer, whatever, any carbonated beverage in a can, or really any carbonated beverage at all. I mean, it doesn't have to be in a can, a bottle too. So let's think about this. You have a seltzer. We use the under 21 example. We have a seltzer or a soda. And once you remove the cap, you hear it fizz and gases come out and you see a bubble. This is Henry's law in action. So initially, if you ever used a soda stream before, so that's how you make your own carbonated drinks. I'm not sure if maybe some of you have done that. My old roommate had one of those. They cost a lot. Like the canisters for the CO2 cost like $70 each. I do like seltzer, so but I mean, I let him. He asked me if he wants to go halves on it. I was like, no, I'm not gonna spend that much. I'd rather just buy seltzer from the store. Anyway, the way you use a soda stream is you are injecting CO2 into the liquid solution. And you're keeping it soluble. At the same time, you're removing or you're increasing the pressure above the liquid. So what this means is that you are forcing the gas particles of the carbonation, the CO2, to be integrated or dissolved in the liquid. This is why when you have a sealed soda or a sealed seltzer, you don't see any bubbles, because the level of CO2 that's in there is underneath the threshold at that headspace pressure. Headspace pressure refers to the pressure above the gas in a solution. So again, you have the CO2 that's in the water, and then you have a lot of pressure pushing down the CO2. This increases the solubility, kind of physically forcing the CO2 to stay in the water. Once you remove the cap, you are very quickly equilibrating the atmospheric pressure around you to the inside of the can or the bottle. What this does is it now drastically lowers the solubility threshold of the CO2 in the water, making most of it come out. Not all of it, but most of it will come out really quickly. If you shake it up, it'll come out even quicker. The reason why, and it'll explode. The reason why is because you are now increasing the pressure of the headspace. So once you quickly put that increased headspace pressure and equilibrate it with the outside environment, it will act like a suction, like a vacuum, and it'll kind of suck everything out. It'll suck all the CO2 out into the atmosphere. And then once that happens really quickly, you get an eruption. So this is how Henry's law works. Are there any questions on that explanation? So now you know how that works. So that's cool. Any questions? We have a question. So why is it that a bottle stiffens up if the CO2 dissolved in the liquid? If there's a limit to how much gas can be dissolved into a liquid. What do you mean stiffens up? Well, I mean, if you add more, so if you add more CO2, then that's, the pressure builds because it's a closed container. So even if you add more CO2 than the liquid would allow, you're still adding CO2 into the headspace, and you're increasing the pressure of the entire bottle. If that's what you're asking, but well, I don't think that's what you're asking. So difference up if the CO2 dissolves. Well, what you're doing is the pressure builds because everything has a vapor pressure. Now, we talked about vapor pressure last class, but basically vapor pressure directly relates to the intermolecular forces. If you have lower intermolecular forces, you're gonna have a higher vapor pressure. That means the amount of the vapor pressure corresponds to the amount of the liquid that becomes a gas, like spontaneously. If you shake something up, what you're doing is you are now speeding up the molecules and you're increasing the amount of gas in there because of the vapor pressure. So you are decreasing the vapor pressure of that solution, meaning more of it's going to be gas, and gases expand. Gases take up more volume than liquid. So it makes sense that the entire bottle will stiffen up and it will build pressure because you're increasing the amount that's a gas form rather than liquid. I think that's what you're asking. But anyway, okay, that's a good question. All right, so Henry's law, the equation for it is C equals Kp, where C is the concentration of the dissolved gas, usually in molarity. K is the constant, and then P is the partial pressure. So the constant varies with the gas, and the partial pressure is the partial pressure of the gas above the solution. So that headspace pressure. So here's what we got for with Henry's law, where if you have a solution, then you have gas molecules. If you increase the pressure, more of those gas molecules will be put in. And if you decrease the pressure, this isn't really showing decreasing pressure, but these are the same picture with different arrows. Anyway, if you increase the pressure, you are forcing those gas molecules to be integrated with the liquid. And if you decrease it, some of them come out. Or if you equilibrate it, it'll be different. But yeah, we get the point. Okay, interactive example. Let's do one. So a certain soft drink is bottled so that the bottle is 25 degrees Celsius. It contains CO2 gas at a pressure of 5 atm over the liquid. Assuming that the partial pressure of CO2 in the atmosphere is that, calculate the equilibrium concentrations of CO2 in the soda both before and after the bottle is open. Okay, so the Henry's law constant for CO2, we'll do this one together. The Henry's law constant for CO2 is, well, we got to look at the unit, is 3.1 times 10 to the negative 2 moles per molarity ATM at 25 degrees Celsius. So Henry's law, we have C equals Kp. So we have the soft drink is bottled up and the pressure is 5 atm over the liquid. Now, assuming the partial pressure is this, so we have partial pressure, calculate the equilibrium concentration of CO2 before and after the bottle's open. So now we know that we got the partial pressure in the atmosphere now. Okay, so we have 5 atm, which is the partial pressure of the CO2 above the liquid. So that'd be our first P. And then we solve for constant. Let's just look at the work, because there's not enough room here. So we have, so what is Henry's law? So we know this is the Henry's law formula. And then of the unopened bottle, you're going to have PCO2 being 5, because that is the headspace pressure of the CO2 in the closed bottle, in the bottle. Then that'll be 5 times your Henry's law constant, which equals 0.16 moles per liter. So that's the molarity of the CO2 when it's in the bottle. Then when you have in the open bottle, the soda eventually reaches equilibrium with the atmospheric pressure of CO2, which is 4 times 10 to the negative 4. So what this means is that we know the final pressure of the CO2 is going to be the same as the atmospheric pressure. So it'll be 4 times 10 to the negative 4 atm. And then your K is the same. And then your final molarity is going to be a lot less, which is going to be 1.2 times 10 to the negative 5th. So this is why soda goes flat after being open for a while. And then because the CO2, the high CO2 concentration from the closed bottle is now having a chance to equilibrate pressures with the outside environment that when it's exposed. So eventually, even the CO2 that's in the liquid after it's opened, because there's still some left over, will come out. And as long as it equilibrates, or it'll come out to the point at which it equilibrates with the atmospheric CO2. And this is what creates a soda going flat. Okay. So temperature effects. So we kind of touched on this, but now we're going to go away from gases a little bit. We're talking about aqueous solutions. So aqueous solutions mean when we have a solid or a liquid that has dipolar ionic interactions, and we're going to mix it with water as a solvent. So solids dissolve rapidly at higher temperatures. That's a key point. So if you put in NaCl into water and you increase the temperature and you mix it around, or you don't mix it around, just increase the temperature, you are increasing the average kinetic energy of the water, thus making it break apart those solid intermolecular forces of the NaCl, and it would be faster. And you would form the new intermolecular forces between the water and the NaCl. This will happen faster at higher temperatures. And then also the solubility of most of them. Solubilities of, it should be most substances decrease. Whoa, wait. That should be increase. Hold on. So that varies. Well, I don't like the statement at all. I don't like the statement at all. Most of them, so the solubility generally increases with temperature for solids into liquids because you have more molecular motion, more increase of making these intermolecular forces. So it varies, but some of them do, some of them don't. Let's see this one. Oh. With gases, that's true. We're not talking about gases here. It's not specific. So, okay. It's true with gases. So let's get to the point. With gases, if you increase the temperature of a gas into a liquid, it generally decreases the solubility. The reason why is because what this does is it increases the speed of the gases, wants to give them more freedom. The gases don't have that tight of an intermolecular bond to liquids when they're in the solution. So they want to leave. If you increase the temperature, they want to leave more. So more molecular motion means they want to get out of there, kind of like boiling almost. So if you increase the temperature, the gases will come out of the liquid more quicker. But for solids, it's the opposite actually. For solids, the amount of solute, and I think this first one describes it. So the amount of solid that can be dissolved may increase or decrease with increasing temperature. Usually it increases. So only for a couple of different solids, it decreases. And there might be a chart. There's no chart of that. It doesn't look like there is, but normally they increase. So to summarize, solids into liquids. Temperature increases, solubility increases. Gases into liquids. Temperature increases, solubility decreases. So that's important, conceptually. Any questions on that? No? All right. Continuing. All right, so solubility of gas and water decreases, increase. Okay, we talked about that already. All right, so rank the following compounds according to increasing solubility in water. All right, so we should be pretty good at this based on what we know about what's soluble in water. Now, what do you guys think? Any guesses? So going from least soluble to most soluble. Good, Isaiah. So you have this is methanol, number 4. That's the most soluble in water because it is the most polar. What comes second? Or what's the second most soluble? Good. 3 is the second most soluble. Nice, because it has, and you kind of get the point. So it has an OH group, which is really polar, and also it has less CH groups, whether they be, in this case, an ethyl group. It has less CHs than number 2. So then number 2 would come next, and then number 1 would not be soluble in water at all because it has no polarity whatsoever. This is butane, N-butane. It's very nonpolar. So the answer is C, D. So it means 1 is going to be least polar, 2 is second, 3 is third, and 4 is fifth. Fourth is fourth. Okay. Which of the following? Oh, I had the answer. So which of the following statement below most accurately describes the effect of increasing temperature on solubility? Now, yeah, which one? So solubility always increases when well, it depends. Solubility always decreases. We can't say that either. Dissolving a solid occurs more rapidly. We could say that. Dissolving a solid occurs slowly. We can't say that. I mean, it's, yeah, so the answer is C. Okay. Aqueous solution of pure water in a closed environment. I mean, we're talking about vapor pressures now. So, yeah, we'll talk about vapor pressures. All right. So the next thing is we talked about what vapor pressure is. And just to reiterate, because we're talking about a lot of different things in the last couple of chapters, vapor pressure corresponds to the headspace or the pressure above a solution, or how quickly it's a measure of how quickly a liquid vaporizes on its own at room temperature. And it could be at different, there's vapor pressures at different temperatures, but let's just say at room temperature. Something like water. Water has a low vapor pressure. What does that mean? That means because of water's strong hydrogen bonds and intermolecular forces, it requires a lot of energy for the water molecules to vaporize, meaning evaporate. Evaporation happens very slowly with water. That means it has a low vapor pressure. Other solvents, like I'm sure many of you have dealt or have seen acetone. Acetone is nail polish remover. If you've ever spilt it anywhere, you notice that it kind of vaporizes almost instantly. You can like wipe it with a towel, it's not even there anymore. That's because of its very high vapor pressure. It's very nonpolar, meaning it has mostly London dispersion forces, which means that there's not much holding it together. And vaporization or evaporation happens very quickly. The same is true with ethanol and methanol. So that vaporizes very quickly. I mean, if you had, I don't know if you went to parties or anything, but if you had like the like very dangerous punches that are like, well, the punches are not that bad, but let's say you have like you're making moonshine, or which is I think illegal someplace, I don't know, but like moonshine is almost 100% ethanol, and that's the ethanol. The alcohol in alcohol is ethanol, and it has a pretty low or pretty high vapor pressure. If you have a liter of it and you leave it outside or leave it in a room, half of it will be vaporized in maybe like 20 minutes. So if you add it to water, that will stop the vaporization from happening. Or if you add it to another substance, that'll stop it from happening. So that's the idea of vapor pressures. So the idea here is now we're going to get into the vapor pressures of solutions rather than just specific solvents. Now, when you have a solution, this tends to strengthen the intermolecular forces, like we mentioned before, of the solvent. So you're adding more intermolecular bonds. What this does is it lowers the vapor pressure, meaning the new vaporization level of the solution is now less because it has more forces to hold it together. So it kind of, this is a good way of saying it, inhibits the escape of the solvent molecules from the liquid because of that strengthened interaction. So that's generally how vapor pressures vary when you put them into a solution, is they decrease. The way there's an equation to dictate how much they decrease by. This equation and this law is called Rayleighs Law. So Rayleighs Law is you can determine the vapor pressure of a solution based on the mole fraction of the solvent and the original vapor pressure of the solvent. So it's kind of it kind of means that the vapor pressure of your resulting solution is the product of the mole fraction of the solvent, meaning how much solvent is actually there, or meaning a scalar factor of the actual partial pressure of that pure solvent. I don't know if that made any sense, but just to say it differently, let's say you have water, or let's say we have something more volatile. Let's say we have like acetone. The partial pressure of the solvent is, let's say it's 0.5. If you have a solution, it doesn't matter what it is. Let's just say it's 0.5. If you have a solution that has very little solute in it, so it's very dilute, is a question I'm going to ask. If we have a very dilute solution, is this mole fraction of the solvent going to be big or small? So there's not much solution, there's not much solute. So this number would be big or small? Close to 1 or not close to 1? Not the opposite. Well, the opposite of small. It'd be pretty big because. So I think maybe I phrased the question. Well, I didn't phrase it wrong, but it's easy to not. Whatever. I'll just explain it. Good try. So if you have a solution, let's say that has 0.1 moles of a solute, and you have 0.99 moles of your solvent, it's going to be mostly solvent. What this means is that the mole fraction of your solvent is 0.99, meaning your partial pressure, or sorry, your vapor pressure of the solution is not going to be changed much. It might be 0.499. The reason why is because only adding 0.1 moles of your solute it created a little bit more intermolecular forces in the solution, but not enough, not nearly enough to change the vapor pressure of the solution by much. So what I'm getting at is that once you increase the amount of solute, you are increasing the amount of intermolecular forces with that solvent, and at the exact same time, decreasing the mole fraction of the solvent. If you decrease the mole fraction of the solvent based on Rayleighs Law, and that's how we came up with this, you're decreasing the vapor pressure. Increasing the intermolecular forces decreases vapor pressure. So I'll say it one more time. Once you increase solute, you are increasing the intermolecular forces, or more generally, the strength of the solution. If you increase the strength of the solution, at the same time, you are decreasing the mole fraction of the amount of solvent in the solution. And what that does, based on Rayleighs Law, is it decreases the vapor pressure. So the more concentrated a solution is, the lower the vapor pressure. That's the main idea of this. Any questions on that? No? All right. Continuing. So we can represent it in a graph, whatever, not really that important. All right, vapor pressure. Let's do an example. So calculate the expected vapor pressure at 25 of a solution prepared by dissolving 158 grams of table sugar of sucrose, molar mass 342, in 643.5 milliliters of water. And they give you a hint at 25, the density of water is 0.9971, and the vapor pressure is 23.1 or 23.76 torr. So for this, calculate the vapor pressure of the solution in torr. So I'll give you 3 minutes or so to do that. So we have the equation, which is P solution equals partial or mole fraction of solvent times the standard vapor pressure of the solvent. All right, so we need the mole fraction of the solvent. Now, how many moles of the common sugar? So we have 158 divided by 342.3, and what is that? That is 0.46. Thank you. 0.46 moles. And then how many moles of the water? So this is water's density of that. So you would do 643.5 times 0.9971 to give you whatever number that is, very close to that. And you would end up with, that's how much it would weigh. And then you would do that number, let's say it's 643 divided by 18, which would give you 36 moles. So the mole fraction would be 0.46 moles of the sucrose divided by 36.46, which is the 0.46 plus 36, which would give you a very small number of what? What do you got? Sounds good to me. Thank you, Harrison. So 0.0127, that would be equal to the mole fraction. All right, so we got everything we need. Take that mole fraction, multiply it by the standard vapor pressure of water, and bada bing, we got our answer. Okay, so we got that, and then we have our 0.46, and then we have that, and then we have our mole fraction. Oh, wait, whoopsie, I made a mistake. We need a mole fraction of our solvent. That's our mole fraction of our solute. My bad. So it's going to be 100 minus that. So, or 1 minus that, which would be 0.998 something. And yeah, 0.987. Whoopsie. So yeah, mole fraction of our solvent. And then that'll be multiplied by our standard vapor pressure, and you get a small decrease in our vapor pressure with the formation of the solution. And that makes sense because look what you're doing. You're adding only 0.46 moles of our sucrose. You're adding it to 36 moles of water. Or is that how much? Yeah, 36 moles of water. 35.6 moles of water. So you can imagine that the amount of offsets can be very little. Okay, moving forward. So lowering the vapor pressure, we can help characterize different solutions. There's non-ideal solutions, which you have, it's kind of different than Rayleighs Law. I mean, it's Rayleighs Law, but you have multiple factors. So let's say you have two volatile liquids that are added together. You would have a double Rayleighs Law. So it would be the vapor pressure of the total solution will be the vapor pressures of each individual component. And this can happen when you have any two liquids mixed together. So it would just be the same thing, but double, just adding them up. And then you have an ideal solution, which is a liquid-liquid solution that, I mean, it's ideal. So, I mean, it's not that volatile, and it obeys Rayleighs Law very well. So sometimes it doesn't. So all these laws that we learn at extreme conditions, they vary. The actual expected or the experimental value varies from the theoretical. So again, like same thing with ideal gases. Okay, so let's do this example. We have a solution prepared by mixing 5.81 grams of acetone, molar mass 58, and 11.9 grams of chloroform at 35 degrees Celsius. The solution has a total vapor pressure of 260 torr. Is this an ideal solution? Meaning, does it obey Rayleighs Law? The vapor pressures of pure acetone and pure chloroform are 345 and 293. So I will give you 5 minutes, or not 5 minutes, 3 minutes to complete this. So basically, the approach would be making two Rayleighs Laws, one for acetone, one for chloroform, adding them up. Do they equal our intended value for idealness? Or what is their value? And if their value is something, then we can tell if it obeys the law or not, or is ideal or not. Okay, so let's do this. Now, we need to figure out the mole fraction of each of these solvents in their own right. Now, acetone, the moles would be 5. That's an easy one. You have 5.81 grams. Oh, these are easy. You have 5.81 grams divided by 58, which would be 0.1 moles. 58.1. And then you have same thing, 11.9 moles of chloroform divided by 119.4. That'll also be 0.1. So we have a identical amount of each solvent added together. So you have 0.2 moles total. Now, what we would do to see if this is an ideal solution is, so we figure out the moles. Then we know that the mole fraction of each one is 0.5. And we would multiply them by their respective vapor pressures of their pure solvent. And we would see, does them added up equal our 260? So it doesn't, it equals 319, which means that it doesn't completely behave ideally as following Rayleighs Law. So that's how you'd figure that out. Any questions on that? No? All right. All right, so we get that. Now the next thing, and one of the last things, well, not last thing, I mean, we still have half the chapter left, but we have colligative properties. So this is not too bad, pretty easy. Colligative properties there's a few of them, that basically the boiling point, and here they are. Here's the three that we're going to learn about. Boiling point elevation, freezing point depression, and osmotic pressure. What happens is that these three factors change based on the amount of solute you have in a solution. And this makes perfect sense compared to, or referring to what we just learned about how a solution, or how solute particles in a solution strengthen the solution as a whole. It strengthens the intermolecular forces. It lowers the vapor pressure. It makes it more energetically stable for the most part in most cases. Why is this the case? And what are other effects that can happen of solution formation? And those are boiling point elevation, meaning the boiling point increases, the freezing point decreases, and the osmotic pressure increases. Or it just changes. It could decrease. Mostly it increases. Now, this is all due to the increasing amount of intermolecular forces in a solution. So there's equations that govern all of these, and let's just go into them. Now, where's the equations at? There they go. So here's one. Well, here's we go. We'll talk about it. I'll put it up here. So here's the equation for both boiling point elevation and freezing point depression. And what this means, boiling point elevation, meaning if you have a pure solvent, let's say pure water, the boiling point is 100 degrees Celsius. If you make salt water, you add salt into that water, it will decrease the boiling point. Or sorry, it will increase the boiling point. The reason why, it will take more energy to now release the water molecules because, release them from liquid to gas, because they now have stronger intermolecular forces with the new solute that's introduced to the solution, the Na pluses and the Cl minuses. So the whole theme of these properties that change when you add solute is that you're strengthening the intermolecular forces, and that causes the boiling point to increase, and it also causes the freezing point to decrease for the same reason. So if something is stronger, more stable, meaning if the solution is more stable and it has stronger interactions, it will take less energy to freeze it, or less energy would be released when it is frozen, because it is at a more energetically favorable state compared to the pure solvent. So what we have is this equation. Delta T equals either KB or KF. Here we have KB. This just means the boiling point elevation constant, and then you have the freezing point depression constant, times the molality of the solute. So that's key. It's molality now. Now, the easy way to do this is you figure out the molality of the solution, of the solute in the solution. The higher the molality, the higher the change in the either boiling point elevation or the freezing point depression. and then based on that constant. The constant is dependent on the solvent. And here is a bunch of different constants for different solvents. So if you have a large molality, meaning a lot of solute in the solution, you're going to have a big change. And this big change, this delta T, is not the new boiling point or freezing point. It is the change that happens from the original. So if you're doing water and you have delta T in your boiling point elevation of 2, and the question's asking for, it'll never ask for delta T. It's going to ask for what is the new boiling point or what is the new freezing point. For that, you have to either add or subtract this delta T to the original boiling point or freezing point, respectively. So for boiling point elevation, the delta T would be added. So if you got 2 for delta T and you're dealing with water, the boiling point of this new water solution, this new aqueous solution, will be 102. If you're doing freezing point depression and you get delta T equals 2, the new freezing point of water would be -2. So does that make sense? And this equation will possibly be given, I think, but it's pretty easy to memorize. All right, so let's do an example. So a solution was prepared by dissolving 18 grams of glucose and 150 grams of water, resulting in the solution that was found to have a boiling point of 100.34. Calculate the molar mass of glucose. That's interesting. So you can figure out the molar mass from this too. So I'll give you minutes. I'll give you 3 or 4 minutes to figure that out. So again, I'll just give you a hint. You have to use the equation for boiling point elevation, which is delta T equals Kb times the molality of the solute. And also Kb for water, I have to give you that, is 0.51. So Kb equals 0.51. Those Kbs and Kfs will be given. So I'll give you a couple minutes for that. All right, let's give it a shot. Okay, so the delta T in this case would not be 100.34. It would be the original boiling point of water minus 0.34. And delta T is always going to be an absolute value. So even if it's the freezing point depression, it'll always be the positive number. And that would be 0.34. And then for water, we have Kb is 0.51. The molality can be calculated from that information already. So the resulting molality is 0.67 moles per kilogram. Now, we know, what do we know about the solution? That 18 grams of glucose was in 150 grams of water. So we know that the molality is going to be the 0.67 equals the moles of your solute, the moles of glucose, divided by your total kilograms of the solvent, which we know it was 150 grams of water. So it'd be 0.15 grams, or 0.15 kilograms, sorry. Then you can calculate the number of moles. And here's the idea. Here's where we're going here. And this example will be on some of the homework questions. If we know the moles and we know the amount that equals that number of moles, so basically we calculate N. What do we get for N? We get N is 0.1. If we know that 18 grams is 0.1 moles, we can figure out the molar mass of how many grams is 1 mole just by multiplying it by 10 or dividing it by 0.1. And we get 180 grams per mole. That's the molar mass of glucose. So they can give tricky questions like this on an exam or on homework and ask for you to identify the molar mass or even identify what type of thing it is, what molecule it is. So yeah, any questions on that? Okay. All right, the next one's freezing point depression. Works identically, the same exact way, but we know that here's how it works. You have ice. The freezing point of ice is going to be 0. Once it goes above 0, it becomes liquid water. But if you have ice in equilibrium with a liquid containing a solid, the freezing point is now lower. And this is because of the strengthened intermolecular forces of the solute. What that does is it means that there's less energy released, because this is more stable than this. There's less energy being released in the freezing of this solution because it's more stable. So yeah, I mean, it goes by the same formula. So here's the freezing point formula. Delta T equals Kf times the molality. Same exact thing. You can use to get molar mass. You can use to characterize different solutions. So you could also, let's say, to give you the question on solve for Kf. That means, and use that information out of a list to figure out which solvent it is. You can do that too. Okay, so calculate the freezing point and the boiling point of antifreeze, that is 50% by mass of ethylene glycol in water. Well, let's just get rid of these answers. Let's get rid of these answers. Okay, so I will give you, you obviously know the answers now, but I'll give you a couple minutes to figure that out. So you can 50% by mass. So you're talking about, you have to remember we did an empirical formula. For the percents, just assume they're grams. So you have 50 grams of ethylene glycol, 50 grams of water. And then you can figure it out from there. So remember I'll write the equations down for both of them. So delta TB equals KB times M, the molality of the solute, delta T, delta TF equals KF times M solute. Okay, so I'll give you 3 minutes or so to do this. So 50% by mass, so you have 50 grams of the ethylene glycol. So the molar mass of ethylene glycol is what? Anybody have that? 62, nice. So 62 grams per mole. So how many moles of it do we have? Good, 0.806 moles. And now we have water, which is also 50 grams, divided by 18 grams per mole of water. Now, what is that going to be? Or do we even need that? We don't even need that. Yeah, we don't even need that. We only need the molarity. Well, it's good to know for another question, but forget it. We don't need that. So now the molality is going to be the same for both of these equations, so we can just figure it out. 0.806 divided by kilograms of solvent. Now the kilograms of solvent, since we assumed 50 grams here, we can say it's 50 grams of the solvent water, 0.05 kilograms. That's 50 grams. And what do we get for the molality? $16, nice. Sounds good to me. So that's 16 M, 16 molal. So that's gonna be 16 moles per kilogram. Okay. Now we can put that into our equations. Oh, I didn't put the constants for you. So KB is gonna be 0.15, so it'd be 16 times 0.51, my bad, times 0.51. So it'll be 16 times 0.51, which is going to equal 8.16. Now this 8.16 is the change in boiling point elevation. So that means our new boiling point will be 108.16. So TB equals 108.16 Celsius. Now for the freezing point constant is 5.12. So we would have 16 times 5.12 equals our delta TF, which is 16 times 5.12. That's going to be, wait, that can't be right. Hold on. Really? Oh, that's for benzene. I was about to say, that's for benzene. That's not for water. Hold on. This is KF for water. Here we go. Water, we have a KF 1.86. That sounds right. So we have, overwrite this. So 1.86. That's going to be 29.76. So that's our delta T of freezing point depression, meaning it's going to be, our new freezing point is going to be negative 29.76 Celsius. Okay, any questions on that? No? All right. So here's another example where you can figure out the molar mass of using the freezing point depression. We already did one using the boiling point elevation, literally the same exact concept. So we can go over that. You can do it on your own if you want. Next one, so why does an addition of a solute to a solvent raise the boiling point? So we did talk about that. Yeah, let's hear from somebody. I've been talking the whole time. Anybody want to give an explanation for that? See who's been listening. Or Eric, if you said something, I don't think I heard you. I saw your mic go up. But yeah, Harrison saves the day. And Daniel, nice. So you have more energy needed to break those bonds, those intermolecular bonds, right? Which then brings the solvent into its into the gas form. It brings the liquid water into the gas form. So yeah, James, good job too. All right, cool. So we got the idea. Oh, there was A, B, and C. I didn't even know that. All right, so solute particles lower the solvent's vapor pressure, thus requiring higher temperatures to cause boiling. That's basically what happens. Okay, so the last colligative property, which is not the same as the other two, it's not the same as boiling point elevation and freezing point depression, is osmotic pressure, and deals with osmosis. So maybe in biology you've heard of osmosis, but what it is the flow of solvent, not solute. When you flow solute, it's called diffusion. So when you flow solvent, it's called osmosis, and it's through a semi-permeable membrane. This membrane has very small holes that permit solvent flow, but not solute particles to pass through. The osmotic pressure results from an increase in hydrostatic pressure on the solution, other than the comparison to the pure solvent. And there's a good chart to describe this. This is not it. Oh, here it is. This one's, I guess, sure. Yeah, this is the one I was looking for. But this also happens too. So let's say you have, and you usually go from high concentration to low concentration of the solute in order to equilibrate that concentration. So let's say you have a solution, right? And you have pure solvent around there in the solution. You put it in a beaker or a flask. This is a volumetric flask. You put it in the middle, and you have a membrane on the bottom. The membrane allows solvent to go in and out, but not the solute. What will happen is there will be a pressure imbalance based on the presence of the solution. What this would do is, because the solution is of higher concentration and the solvent has no solute concentration, the water or the solvent would want to move from low concentration to high concentration in order to equilibrate those concentrations. So it'll make an attempt by moving the water into the beaker, diluting the solution and making it closer to zero concentration. And over time, this difference would be the osmotic pressure, because normally there's no difference in the heights of the liquid or both the liquids. Then the difference in the height, we know this doesn't work in nature. There is a pressure gradient. There's a pressure differential from this liquid to this liquid. That pressure differential is called the osmotic pressure, the pressure induced by the osmotic forces. So if you apply pressure to a solution, the pressure required to stop this process is another way to measure the osmotic pressure. So, I mean, that's how they really measure it. They They try to keep those water levels the same. The pressure required can be read on a dial or a pressure or barometer, and that is the amount of pressure, that is the osmotic pressure. And there is uses of it, which are very similar to the other one, calligraphy properties. You can characterize a solution, you can determine the molar mass, and a small concentration of solute produces a relatively large osmotic pressure. Well, that's beside the point. But here's the equation. So the equation is a little bit different. You have capital pi, maybe you haven't seen this one before. This is capital pi, equals M, which is the molarity, R, which is our ideal gas constant. Hey, we're back. Because it has to do with pressure, right? Ideal gas constant. And this ideal gas constant is the same one we've been using, 0.08206 liter mole or liter ATM per Kelvin mole. And T is our Kelvin temperature. So this is the equation for osmotic pressure. And you can imagine, because you have molarity, moles per liter, you can figure out the molar mass of an unknown solute and other things. And you can figure out temperature, and you can figure out the identity of it by the osmotic pressure. Okay, so here's a question, determining molar mass from osmotic pressure. To determine the molar mass of a certain protein, that 1 × 10⁻³ grams, or 1 milligram, is dissolved in enough water to make a 1 milliliter of solution. The osmotic pressure of the solution was found to be 1.12 torr. Calculate the molar mass at 25 degrees Celsius. Calculate the molar mass of this protein. Okay, so I'll give you a couple minutes to do that. And then here's the formula again. Capital pi equals M, which is the molarity, times R, which is our ideal gas, 0.08206, and our temperature in Kelvin. All right, let's start working on it. Now you have the osmotic pressure, and keep in mind, this R constant is what? 0.08206 in ATM, right? ATM, liter ATM per Kelvin mole. So that means torr has to be converted. So 1.12 divided by 760 would be our pressure. So maybe that, because in the previous ones, we didn't have to do that, but now we do, because now we're using the ideal gas constant. So 1.12 divided by 760, that's going to be 0.00147 ATM. So that is going to equal our molar, or our molarity, times 0.08206 times our temperature, which is 25, or 298. So what did you get for the molarity? Did anybody solve for that? Or did that trip everybody up with the torr, converting that to ATM? Gotcha. Okay, so I will just go over here. So we have our values, our variables. Now we can find the molarity, and we find it as 6.01 times 10 to the -5th molarity, moles per liter. And then from that, we know that the molarity is the moles per liter, right? So we know that, we know that 1 milligram of it was used. So we know that 1 milligram was dissolved in 1 milliliter. So that the mass of the protein per liter is 1 gram. Now we know, based on molarity, that 6.01 times 10 to the -5th, which is the molarity we found, moles per 1 liter, would equal 1 gram of the protein. So 1 gram of the protein is this many moles. So what we do to find the grams per mole is we very simply divide. We divide 1 by 6.01 times 10 to the -5th. Does that make sense? Is there any questions on how I did that, or why I did that? No? All right, so you divide those, and then you get your molar mass, which is 1.6 times 10 to the 4th. This makes sense. relatively small protein. Proteins range from 10,000-ish to over 100,000 grams per mole. So this is about 16 grams per mole, or 16,000. So that makes sense. Okay, the last kind of thing we're going to talk about is dialysis. It has to do with osmosis, kind of, but I mean, it's instead of the solvent moving, it is the solute moving. So what dialysis is I mean, it occurs in really a lot of membranes in our body, and it occurs in our kidneys. So what happens is in our kidneys, our blood is filtered in our kidneys constantly. So our blood, when it goes around our body, it has different oxygenating substances in it. It has oxygen radicals. It has it can have other things in it. Our blood is a mixture. It's a solution. So what would happen is the blood from our body that's been circulating comes into our kidneys, and we have ions and just essential molecules that are going to be in the blood and we have this dialyzing solution. So in the kidneys, we don't have a dialyzing solution. It's kind of just like saline. And what happens is the blood flows through and we have dialysis occur. Meaning because of the low concentration of solutes on the outside of the membrane, the solute particles will move from high concentration to low concentration to equilibrate that pressure, or that concentration gradient. So the thing, again, that causes everything in nature to happen is gradients, whether they're energy gradients, pressure gradients, like for wind and weather, whether it's concentration gradients for any kind of solution movement, or osmotic gradients for water movement, which really, that's the key telltale thing of every movement, natural movement in nature. Reactions or energy gradient. So anyway, the waste products and different ions that are not supposed to be in the blood are dialyzed out. So that's how dialysis occurs. Then the purified blood is moved out into the body and circulated again. Then it keeps getting repurified. So this is what keeps our blood healthy, because we circulate the same blood for weeks at a time without the blood cells before the blood cells die and we get new blood cells, but it's weeks at a time. So we want this blood to be constantly replenished, especially when we have off days and we have cheat days and we're eating like crap. So, or if we're drinking alcohol, that we don't want the alcohol to always be in our blood, right? That's why our kidneys are essential to getting rid of the alcohol in are lowering our blood alcohol content. So, so if your kidneys don't work, you have dialysis machines, which are basically an artificial kidney, which can use a dialyzing saline solution, and it flows your blood, it circulates your blood through this bucket basically, and well, into the tube. But then the tube is in a bucket. The tube is a semi-permeable membrane. The semi-permeable membrane will allow the bad particles to enter the dialysis solution and leave your blood. And meanwhile, the purified blood will go out, and this will keep recirculating. And then eventually it'll get to a point where the dialyzing solution will kind of it'll slow down this process, because the concentration of the dialysis solution will be around the same as in the blood. So what you do, you remove the dialyzing solution and you put in another dialyzing solution that's clean, so you can redo this process again. So this is the process of dialysis. Now, what we can talk about with dialysis is this concept of isotonic, hypertonic, and hypotonic solutions. Now, this has to do with osmotic pressure. And it more talks about, rather than solute movement, it talks about solvent movement. And this is really corresponding to blood cells and really cells in general. Now, an isotonic solution means that the solution on either both sides of the membrane have an identical osmotic pressure, meaning there's going to be no net movement of solvent. Hypertonic, and I'll show you examples of these two. Hypertonic means that they have the osmotic pressure is higher than that of the cell, or one side of the membrane. And hypotonic is where the osmotic pressure is lower than that of the cell. So here's our example, hypertonic. What will happen when you have a hypertonic solution and you have a cell, what will happen is the water will flow out of the cell. The reason why is because in hypertonic, the concentration of the outside material or outside solution is higher. Hyper means higher. Hypertonic meaning higher concentration solution. What will happen is, because it's higher, in order to attempt to dilute that solution, the water within the cell will move outward and will attempt to dilute that solution to lower that concentration gradient, because concentration gradients aren't favorable. The concentration wants to be equilibrated. So in essence, what will happen is the cell will shrivel up, or what we call crenate, meaning the water will leave the cell in an attempt to dilute the outside solution, which is a higher concentration, or hypertonic. Hypertonic. Any questions on that one? No? All right. And then the other one is hypotonic. So a hypotonic solution is where the concentration on the outside is lower than the inside. In this case, it causes a swollen cell and it could even rupture. The reason why, and this is called hemolysis, the reason why, that's more for blood cells, but the reason why is because in the same thing is happening where the water from the lower concentration environment on the outside is coming into the cell in order to dilute the higher concentration inside in order to make the concentrations equal. Most of the time this can be achieved, but if it can't, water will keep flowing in until the cell actually ruptures and the cell membrane will break. So that's called a hypotonic solution, meaning the solution around the cell is at hypo, meaning lower concentration. This will move solvent into the cell to try to equilibrate those concentrations. Any questions on that one? No? All right. So consider the setup in which pure water is separated from aqueous sugar solution by semipermeable membrane, which allows the water to pass freely, but not the sugar. Oh, which allows, yeah. So I'm not asking a question. I said it in the form of a question. So which allows water to free pass it, but not the sugar. After some time passes, what will have happened to the concentration of the sugar? So the pure water is separated from the sugar by the membrane. Now, what will happen to the sugar? A. So we have A, and that's not right. Not C either. So it'll be B. All right, so let's talk about it. All right, let me just wrap my head around this one. So consider it's late. So consider a setup in which pure water separated from an aqueous sugar solution by semipermeable. Okay. Which allows the water to pass freely around the sugar. At some time pass, what will happen to this concentration of the sugar? Okay. So here's what they're talking about. Well, let's say we have, so the answer is B. So we already established that. Here's what's going on. So let's say we have one of these. And on one side, I can't write on it, damn it. Okay, here, we'll do this. Okay, on one side we have sugar and water. And on one side we have just water. So what will happen is, so sugar, pure water is separated from an aqueous sugar solution by a semipermeable membrane. Okay, so what will happen is the water will be like, oh, I need to equilibrate. This is too high concentration over here. There's a gradient. There's a large concentration gradient. In order to offset this gradient and this will create osmotic pressure, the water will move because the sugar can't move here. If the sugar could move here, it would do that. But the sugar can't. Only the water can move in the semipermeable membrane. So the water will move this way, the water level here will decrease, the water level here will increase, thus diluting the sugar. They'll try to make it as close to concentration as the pure water as possible, diluting it. So good job, Eric. It will dilute it and it will increase or decrease the concentration. So I think it's just flipping the ideas. So dialysis, the dialysis is when the solute moves. Isotonic, hypertonic, osmotic pressure is when only the solvent moves. So solute is for dialysis, solvent is for osmotic pressure. So only the solvent can move to offset the concentration gradient. In that case, the pure water would have to move into the solution into the solution, the sugar solution, in an effort to decrease this concentration enough. Okay, so what concentration of sodium chloride in water is needed to produce an aqueous solution of isotonic with blood? So isotonic with blood, meaning the osmotic pressure is 7.7 and at 25 degrees Celsius. So what concentration? We can use our osmotic pressure formula, MRT. We know our osmotic pressure is 7.7. Our molar mass is unknown, which we're trying to figure, or sorry, our molarity. We have our R, 0.8206, and our temperature is 298. We can divide and figure out M, and M is equal to 0.315. Okay. But there's one more, okay, so there's one more important thing we didn't learn. So for all of these things, I don't know why they went through it. They should have went through it first. But for all these things meaning colligative properties, osmotic pressure, boiling point elevation, and freezing point depression, they are all responding to the number of solute particles, not compounds, not molecules, or not molecules, just particles. So what I mean by this is that if you have something like NaCl, and lately, so you notice for all the examples, we've only been talking about a protein, a sugar. We've never been talking about different salts. The reason why is because something's different with these salts. The sodium chloride, when it's in water, how many particles is it? It's the Na plus and the Cl minus. It's 2 particles. These properties correspond directly to the number of particles, or the molarity or even molality of the particles in the solution, not the absolute number of molecules that were first introduced to it. So for example, FeCl3 has 4 particles. It has iron, 3 plus, and then Cl minus, 3 of them. Even though it's 1 molecule, it has 4 particles. So what this means is that our answer we got for this question, as our molarity of the particles is 0.315. Remember, this is molarity of the total solute particles. What did I do? The total solute particles. In order to figure out the molarity of the NaCl required for this, we'd have to divide it by 2. Because a solution of 0.158 molarity would give us 0.315, or double the amount of molarity of NaCl, of particles. It's solute particles. So does that make sense? That concept makes sense. So the more molality or molarity of particles we have, that directly determines the colligative property value, whether it's be the boiling point elevation, freezing point depression, or the osmotic pressure. Any questions on that? All right. So now the finality, wow. The finale of that is we can modify these equations a little bit by this thing called the Van Hoff factor. The Van Hoff factor is denoted as I, and it provides a relationship between the moles of solute and the particles in the solution. Basically, it's an integer, and it corresponds to the number of ions. If you have a non-electrolyte, something like a sugar, the Van Hoff factor would be 1. We've seen that in all of our examples so far, except for the last one. NaCl would have a Van Hoff factor of 2. FeCl3 would have a Van Hoff factor of 4, because it corresponds to the number of particles per molecule that are going to be ionized or broken apart when they're in the dissolved solution. So what we can do is we can multiply our Van Hoff factor when necessary in our different colligative properties. So Van Hoff factors, just to give you an example, the observed varies, but the expected one we can go by. So MgCl2, it would be 3. MgSO4 would be 2. Glucose would be 1 because it's a non-electrolyte. HCl would be 2. FeCl3 would be 4. So it's basically the number of particles that will be dissolved from the molecule. And we can modify these equations by multiplying by the Van Hoff factor. So for freezing point depression and boiling point elevation, it varies, because if you have double the amount of molecules, if you're dealing with NaCl, you have double the amount of molecules. This means that there will be 2 times the amount of change in the freezing or the boiling point. Same thing for osmotic pressure. If you have an osmotic pressure, but you have double the concentration of molecules on one side, this will double the osmotic pressure because twice as much water will move from one side to the other. So that's important to mention. That it's very important. The complete equation for all of these different colligative properties has to do with the Van Hoff factor, with I. So that's the complete equations. Now, are there any questions on that? That's very important to complete the equations, kind of bringing the whole picture together here. No questions? All right. So we'll do one. So we'll do osmotic pressure again, and then we'll be done. So the observed osmotic pressure for a 0.1 molar solution of Fe NH42 SO42 at 25 degrees is 10.8 atm. Compare the expected and experimental values for I. All right. So what would be the Van Hoff factor for this? What do you think would happen? What would dissolve? How many particles? Five. Good. 5. You'd have Fe. You'd have 2 NH4s. You'd have 2 SO4s. So that's going to be 5 equals I. So compare the expected and the experimental. So the expected is going to be 5. Now let's figure out the experimental. So the observed osmotic pressure is 10.8. So 10.8 equals M, which is the molarity, 0.1, times your Van Hoff factor, I should put that in the front, I, times your R, 0.08206, times your temperature, which is 298 Kelvin. So what we're doing is we're calculating the observed Van Hoff factor. So we would divide 10.8 by everything on the right, and we would figure out that it's 4.4. So it's close, it's less. And the reason why it could be less, it's usually never more. Are there any examples where it's more? Yeah, it's usually never more. The reason why it's probably going to be a little bit less is because some of these ions or some of these molecules or particles are going to be paired still. They're not going to be 100% dissociation. And they're going to be paired up with their ionic partners still. So like you might have some Fe mixed with some sulfate in there, but it'll be to some level. And you could always tell experimentally. So yes. So that's about it.